All right, up here, please. Hi. Okay, so we have a relation defined by just these 4 points, right? It's not a formula. It's not a continuous graph. It's just 4 points. And if I was going to plot them, right, if I wanted a graph of this function, it would just be 4 points. 2, 4, right? Just those 4 points. You don't connect them, right? It's just those 4 points. All right. What are the domain and range of this relation? So what x values does this function live on? -2, -1, 1, and 2. Right? It's not the interval from -2 to 2 because the function doesn't live on, say, 1.5, right? So it's not all the numbers between -1, -2, and 2. It's just the integers. So you just list them. And then what's the range of this relation? 4 and 1. Those are the only y values where the function lives. 4 and 1. You don't need to write the repeats. Okay, now I'm going to reverse the components of each ordered pair, and the result will be an inverse relation. Okay, so my ordered pair is, instead of -2, 4, I'm going to have 4, -2. Instead of -1, 1, I'm going to have 1, -1. Just swapping the x and the y coordinates. 1, 1, when you switch it, stays 1, 1, and 2, 4 becomes 4, 2. So there's my new relation. This is the inverse relation where I swapped x's and y's. What's the domain of this inverse relation? 4 and 1. And what's the range? Okay, so do you see how the domain and the range of the inverse relations are related? They changed? Yep. Yep. Is this inverse relation, this guy, is that a function? Why not? Yeah, because there are x values that have more than one y value associated with them, right? For 4, the x value of 4 shows up twice, and it's associated with -2 and 2. So one x can go to only one y for it to be a function. So this is no, because 4 is sent to 2 different numbers, right? -2 and 2. And 1 also, right? 1 also is associated with 2 different y's, which makes it not a function. So a function whose inverse is also a function is called one-to-one. Okay. Is the relation that I gave you at the beginning, is that a one-to-one function? No, because we just said its relation is not a function, so this is not one-to-one. Good. Okay, so basically we've already answered this first question. Does every function have an inverse function? And how can we tell? So we started up here, we started with a function, and its inverse was not a function. So the answer is no. Every function does not have an inverse function. But let's look at another example. F of x equals x plus 1, g of x is x minus 1 squared. So here are 4 points on f of x. Right? If I put a -2 in for x, I get -1 for y. So these are just 4 points on f. And if I reverse them, I get this. Right? So when I reverse them, do I see any problems? Are there any x's that are associated with more than one y? No. So this seems fine. So this is a function, and the inverse looks like a function, right? So for the function f of x equals x plus 1, different inputs produce different outputs. The inverse is also a function. Okay, so now I'm going to look at 4 points on x minus 1 squared, right? So let's say if I plugged a 0 in for x, the y value would be what? Looking at that formula. Put a 0 in for x, what do you get? 1. So that's why I have the point 0, 1 listed there. When x is 0, y is 1. If you put a 3 in for x, what do you get? 4. That's why the point 3, 4 is listed there. Those are just 4 random points that I picked on the graph of G. If you reverse the components, reverse the x's and the y's, Do we have any issues? Yeah, which one? The 4s. I now have an x value that's associated with 2 different y values. So this is not a function.
If you had the same in the original without reversing, if you had the same range on 2 of them with different domains, it's not going to be a function.
Yeah. This first guy, was this a function? Yeah, so this one was okay, but its inverse is not. Okay. So for the function g of x equals x minus 1 squared, certain inputs produced the same output, like -1 and 3. 2 different inputs gave the same output. That's okay in terms of whether or not this thing is a function, but once you reverse the components, its inverse is not a function, because that repeated output becomes a repeated input, and now it's not a function. So the inverse of g is not a function. So when we swapped the inputs and outputs for f and g, we noted that the inverse of the linear function, f, was a function, but the inverse of the quadratic function, x minus 1 squared, was not a function. So if I look at the graphs of these things, this one is f, and this one is g. Okay. I want to see if I can use the graph to tell me whether or not the inverse will also be a function. Okay. So if I draw a horizontal line at y equals 4, here's y equals 4, horizontal line. Okay, did that. How many times does that line intersect the graph of f? Once, because f is just the straight line here. I'll do f in pink. There we go. So once. How many times does that line y equals 4 intersect the graph of g? Twice. Yep. So it turns out that if any horizontal line, like the one we just drew at y equals 4, if any horizontal line intersects a graph at 2 or more points, then the graph of the function will not have an inverse function. Okay. And we refer to this as the horizontal line test. Okay, so the last thing for today's demo is how to find the inverse of a function algebraically. Okay, so if a function is defined by an equation, we can get an equation for its inverse by just changing the role of x and y and then solving for y. So your textbook refers to this procedure as the switch and solve strategy. So here are the steps, right? We have f of x equals 5x minus 6. That's my function f. I would like to find a formula for the function f inverse. So first you should verify that the function is one-to-one. That's most easily done by looking at a graph. And what does the graph of 5x minus 6 look like? It's a line, yeah, because it looks like mx plus b. This is a line, so this is the graph of a line, which means it passes HLT, right? It will pass the horizontal line test. Whoops. It'll pass the horizontal line test because it's a line, right? Okay, so the next step in my procedure is to replace the f of x with a y. So I have y equals 5x minus 6. Next step, interchange x and y. Wherever you see a y, write an x. Wherever you see an x, write a y. This is going to become x equals 5y minus 6. Then solve for the y. Get the y by itself. So I'm going to add 6 to both sides and divide by 5. Maybe I should write out the steps because it won't always be that easy. Plus 6, plus 6. I have x plus 6 equals 5y. Divide by 5, divide by 5. And I get y equals x plus 6 over 5. And I left out a step. Oops. The very last thing you do before you check for A should be replace y, replace y with f inverse of x. So f inverse of x is x plus 6 over 5. So there it is. We found the formula for the inverse function. So you switch the x's and the y's and you solve for y. That's it. And then you should verify the result by composing your original function, y equals 5x minus 6, and your inverse function, x plus 6 over 5. Remember, composing means plugging one into the other. So we're going to do that out because I know that that's something that's been sort of a sticking point for a lot of people. So I want to do f evaluated at f inverse of x. So right above here, I'm just going to write the formula for f of x. F of x is 5x minus 6. What? Oh, okay. Yeah, so then instead of 5x minus 6, because I replaced the x in parentheses in that formula with f inverse of x down below, right? It's f parentheses x becomes f parentheses this thing, right? So in the formula 5x minus 6, I have to replace the x with what I replaced the x with in parentheses. So this is going to become 5 times f inverse of x minus 6. Right? But then f inverse of x actually has a formula that we just found. So I'm going to replace f inverse of x with its formula. So this is going to become 5 times x plus 6 over 5 minus 6. And then these 5's cancel. And I have x plus 6 minus 6, which is x, which is what I am looking for. I want when I compose them to get x. That's the definition of an inverse, is that when whatever you plug in, if you apply f and then f inverse, they undo each other. So if you plug in an x, you get an x back.
So we're just verifying.
Yeah, we're just verifying. Yeah. Some people like to verify with a number first, right? Like if I plug in, let's say if I did f of 2, what do you get? Remember, this is my formula for f. Yes, 4, right? And then I'm going to do f inverse of 4, right? I'm going to plug 4 into the formula I got for f inverse. And what am I like hoping I get if I did everything right? 2, right? The thing I started with. I put a 2 into the f machine, I got a 4. I want to put a 4 into the undo machine, so I want to get a 2 back. And you totally do. Yeah, if I put a 4 in here, 4 plus 6 is 10 over 5 is 2. Right. So I get a round trip, at least for 2, I get a round trip. So it's a good indication I did it right. That's it. You guys try.